All right, hello and welcome to lesson 7.3. It's a mix of 7.2, which was a GeoGebra lesson. We're going to go through some circle conjectures while we use GeoGebra. So we're going to start with GeoGebra on this. I'm going to first construct a circle, and then I'm going to go over and use this tangent. I want to construct a tangent line to this circle. So remember, a tangent line only crosses at one point. So far I have my tangent line. And next, I want to construct the radius to the tangent line. Okay. And I need to construct a point on there. All right, so I've constructed my radius and my tangent line. And I want you to just look at that angle and think, what type of angle measure do you think is between the tangent line and the radius, so between those two? So we're going to test it out by measuring that angle. Oh, I always do it backwards, remember. Let's measure it the correct way. Okay. So, and it shows up as a 90-degree angle. So our first conjecture is a tangent to a circle is perpendicular to the radius drawn to any tangency. So if I look at this, if I draw another tangent line, let's say, oopsie. If I draw another tangent line, and then I draw the radius going towards it, that will also be at a 90-degree angle. So any tangent line drawn to a radius from the point of tangency will meet at a 90-degree angle. All right, now I'm going to go back to GeoGebra and we're going to discover the next property. So I'm going to leave that up there and I'm going to draw another tangent line. Okay, so I'm going to pick a point over here and draw another tangent line through this point, tangent to that. All right, and I'm going to look at these two segments here. I want to look at the segment from the intersection of these two to the point of tangency. So that segment is, look over here, it's 2.46, and, oops, wrong point. I want to measure from, I need to move C. Hold on 1 second. I gotta get this one to move point C. All right, so I want to measure, I measured E to point B, and now I'm going to measure from here to here, and it's 2.62, and I think that one got undone. So our whole goal was to look and see that this, from the point of tangency to the intersection and the other point of tangency to the intersection, is congruent. So our picture should look something like this, and it says tangent segments to a circle from a point outside the circle are congruent. So if you look at this picture, these two are congruent, and both of these are radii. So that's a radius, so those two are congruent to each other as well. So the shape we've created here is a kite, and we also know from the previous one that these must meet at a 90-degree angle. If you look at my lovely 90-degree angle. All right, now we're not going to use GeoGebra for the next one. We first need to recall what a central angle is. So a central angle is an angle that starts at the center, and it contains two radii. So here's a central angle. And let's say that angle is 29 degrees. All right, if that angle is 29 degrees, there's a different, yesterday we looked at arc length. Now we're going to look at just the measure of the arc. So the measure of the arc is actually just an angle measure. And so what this says, it says the measure of the intercepted arc is the measure of its central angle. So that means that the measure of this arc is also 29 degrees, right? The second one deals with an inscribed angle. So in this inscribed angle, it says the measure of an inscribed angle in a circle is half the measure of the arc it intercepts. So recall, when it says the measure of an arc, we're just looking for an angle measure, not an arc length. So, and recall that an inscribed angle starts on the circle and contains the two chords around it. All right, so I'm going to draw another practice one. So I draw another circle over here. And I have an inscribed angle, let's say, like that. Let's say that this is, that the arc it intercepts here and here let's say that the measure of that arc is 100 degrees. Now let's go backwards and find this measure right here. Well, that means that this measure would be half of it, so it'd be 50 degrees. Okay, so the inscribed angle is half the measure of the arc. Right, we're going to go back to GeoGebra now. I'm going to construct a new one here. So if I have this, I'm going to construct a new picture. I'm going to construct a circle again, because again, the whole chapter is dealing with circles. And I want to construct any chord. So I'm going to pick any 2 points on here. We'll just use those 2. Right. And I'm going to construct the perpendicular to that line going through the center. I'm going to construct perpendicular to that line going through the center. Now let's find the intersection of that point here. It's D. And I'll make a conjecture right now in your head. What do you think the distance from C to D is? And what do you think is true about the distance from D to B? So what I'm guessing is you're looking at them saying those look very equal. So let's measure the distance from here to here. That's 1.13 and that's 1.13. So our next conjecture is the perpendicular from the center of a circle to the chord is also the perpendicular bisector. So looking at this picture, same as ours before, we found that this side is congruent to this side. So if I drew any other chord, let's say that one. Let's make it a little straighter. Okay, and then I drew the radius perpendicular. Okay, a little straight. So if that was a perpendicular, I know that this side is congruent to this side. That's all that property is saying. All right. And we don't need to do another GeoGebra for the next one because the opposite is true. When you have a perpendicular bisector of a chord passing through the center, the perpendicular bisector of a chord must pass through the center. So if we go back, when we constructed that GeoGebra, we constructed the perpendicular to the chord through the center. Well, if I were to construct the perpendicular bisector of this, this segment, notice another line doesn't appear because it's the same thing. So the perpendicular bisector of a chord passing through the center of the circle must be the same thing as the perpendicular bisector of the chord. So any perpendicular bisector of any chord, so if I drew another chord, let's say up here, if I drew the perpendicular bisector, meaning it has to cut it in half, so that looks like it's about in half, and it has to be perpendicular to it. That line must pass through my center always. Okay, so the last thing we're going to do, the last property we have is we are going to look at parallel lines. Okay, so I'm going to pick 2 points on this circle and construct a line, and I'm going to pick another point there. So I'm going to construct one line, and then I'm going to construct a parallel line to this line through my other point. Now if we look at the measure of arc DB and the measure of arc C, let's create that last point there. We want to intersect those two. And CE, those look like they're very congruent to me. So let's check and see if they are congruent. So that's 1.27, and that's also 1.27. So if you notice the parallel lines make congruent arcs. So our last property is parallel lines intercept congruent arcs on a circle. So if you look at the picture, it's congruent here. It's congruent here. Okay. And these two parallel lines also form congruent arcs. So now we're going to start off with some examples. For each example, I want you to try it on your own using the properties we just learned, and then come back for the answer. All right, so this one's pretty short. This goes back to that property. The measure of the central angle is the same as the measure of the arc, so x equals 127 degrees. That one's pretty short. The next one says if the radius is 8, find the arc length of x. So remember, the measure, when this one says find the measure, that's different than finding the arc length. They will tell you to find the arc length if they want you to find the arc length, and they will tell you to find the measure if they want you to find the angle measure of the arc, or the, right? So this one goes back to yesterday. Remember, it's the angle divided by 360 equals arc length divided by circumference. So I'm going to, if I know the radius is 8, I'm going to write that on there. So go ahead and see if you can set this up. All right, so I hope your setup looks like 127 over 360 equals, I don't know what my arc length is, so I'm going to call it x, over the circumference. The radius is 8, so the diameter equals 16, so the circumference equals 16 pi. Right, again, the fastest way to solve, cross multiply. So I'm going to go to my calculator here. 127 times, what was it? Times 16 is 2032. So I get 2032 pi equals 360x. To finish solving, I'm going to divide that by 360. Right, so my arc length is going to equal, divide this by 360. And I get 5.64. So my arc length is approximately 5.64. Okay. All right, we have about 2 more examples for today. This one goes back to the inscribed angle property. So the inscribed angle, remember, is half the measure of the arc. Well, in this case, we have the inscribed angle, okay, which is 53. So instead of halving it, we're going to double it, and I get the measure of the arc to be 106 degrees. Okay, so the next one again is going to be from yesterday. The radius of the circle is 10 meters. Find the arc length. Now this one requires us to find the central angle. So there's my angle. So on the previous one, I learned that x is 106. So I also need to use the property that the measure of the arc is the same as the central angle. So the central angle on this then is 106 degrees. So to set this up, I know that my radius here is 10 meters right here. Okay, so I'm going to do 106 over 360 equals my arc length, which I don't know, over my circumference, and since my radius is 10, my circumference is 20 pi. Now notice this asks you to find arc CB there, excuse me, going off my arc here. Not very good at straight lines. All right, so that arc there is a minor arc, so the angle we're looking at is 106 because that's the arc, or the angle that creates that arc. So again, see if you can solve this, cross multiply. So I'm going to do it all in one step. I get 106 times 20 in my calculator, and in the end I'm going to have to divide by 360. So I'm going to do 106. Oopsie, I always forget to take my pen off. 106 times my 20, and I'm just going to leave the pi off for now, and then divide by 360. So my answer is approximately 5.89 pi. So my arc length here, 5.89 pi. Okay. All right, and this is going to be our last example for the day. It says find the degree measure of arc CB. Okay, so arc CB Remember, if it has two letters, it has to be a minor arc. So if I look this way and think that's arc CB, going here, right? That can't be it because that's bigger than half. So I'm not looking at that one because I would need three letters. It would need to say arc CDB, but that's not what I'm looking at. I'm just looking at CB, so it goes like this. So that's the arc I'm looking for. So first, I know what this arc is. Let's call that X. It's double the inscribed angle, so that would give us 208 degrees. But I really need to find that blue part over there. So in total, so I know that this arc here, oh my goodness, is 208 degrees, but I'm not trying to find that one. So what I have to do is subtract it from my total of 360. So 360 minus 208 leaves me with 52 degrees as my, not 52, 152. Okay, 152 degrees for that arc. Is that the last example? All right, we will finish the rest of these examples in our next lesson. Hope that helps.